Okay, welcome everyone to TAMIDS Spring 2021 seminar series. And today I'm very pleased to introduce our speaker, Dr. Pascal from Hentenryck of Georgia Tech. We actually invited Pascal last year for his seminar, and was later canceled due to that week of the initial part of the COVID-19 impact, and so Pascal's seminar is delayed for almost the entire year. And Pascal is the Russell Chandler the third chair professor in the School of SYE at Georgia Tech, associate chair for innovation and entrepreneurship, director of the Socially Aware Mobility Lab. Pascal's research focuses on data science and optimization with many applications like in mobility, energy, and resilience. Several of his optimization systems, including CHIP and OPL, has been in commercial use for more than 20 years. And Pascal himself is an Informs Fellow and IEEE Fellow. And today he will talk to us about end-to-end data science. So Pascal, we are very delighted to have you eventually, and the platform is yours, and whenever you are ready.
Yeah, thank you very much, Hugh, and thank you again for the very nice invitation. Just a year, too late, but I think one of the good silver lining is that you'll see even more progress on some of these applications. So I'm going to talk about end-to-end data science, and in particular, end-to-end learning and optimization. And the motivation here is coming from the fact that there is currently, I think, a large amount of exciting topics at the intersection of AI and OR. And that's what I would like to focus on today. So as you know, AI in the past has really captured the public imagination by solving, games like AlphaGo, beating the world top players. I was very surprised to see a computer beat, Jenkins in Jeopardy. And those have really captured the imagination of the public. Some of these applications are now used every day in computer vision and also in natural language processing. But what I was wondering is that, can we actually do very similar things in engineering domains? Can we actually look at electrical engineering, in manufacturing, in healthcare, in civil engineering, and do very similar kind of contribution by marrying data science, machine learning, and optimization? And so what I want to show you today is a number of things that we have done in those topics. So I want to talk a little bit about ride-hailing system. I want to talk about on-demand transit system. I want to talk about energy systems and also census data, and give you a sense of the role of optimization in many of these topics and the convergence between machine learning and optimization. Now, these are a massive number of topics, so I won't go into details about every one of them, but what I hope to achieve is to give you the sense of what we can do and the kinds of exciting topics that are emerging and for which there are a lot more developments that are possible. So let me start with one of the topics which is in ride-sharing systems and learning optimization models. So you're going to see a combination of machine learning, optimization, model predictive control, and then at the end, learning these optimization proxies. So ride-hailing system at some point were seen as the way to solve all the transportation problems in the city. I live in one city which is one of the worst in the US. Before the pandemic, it was a 24/7 congestion, traffic jam essentially. And it's getting there back again. And one of the things that people have recognized now is that many of these ride-sharing systems have done is increase actually congestion in many cities. So they have increased congestion by 62% in San Francisco compared to what would have been happening if there were no TNCs. This is a very nice study by some of my colleagues in San Francisco and Kentucky. And so cities have been banning, or at least limiting some of these ride-hailing systems. And so the interesting point is that if you move a little bit from having one person in one car, and if you start moving to ride-sharing, you can make a very substantial difference. So this was a study by people at MIT, and they showed that by looking at the taxi data in New York City, they could actually serve the demand of 98% of the riders in New York City using 3,000 vehicles instead of 12,000 with a very small waiting, average time. Now, one of the things that they don't do is guarantee a right. And so we started looking at this and trying to design a system like this where people would have service guarantee. They would always be able to get a right. And also the fact that the right that they would get would not exceed too much, would not exceed the right that they would have get if this was a direct trip, for instance, not more than 50% of the duration. So we wanted to look at a system like this, obviously doing ride sharing, but enforcing these two constraints. And obviously the objective for us was minimizing the average waiting time because we would serve everybody. A secondary objective was also to make sure that nobody is waiting too long. And this is actually very important because otherwise some people can take 15 minutes to wait, and that's not a reasonable quality of service. The computational challenges when you try to do something like this is that in a city like New York City, you have about 1 million of requests, some of the days. And so this is like servicing 500 requests every 30 seconds. So this is a really interesting computational challenge. So what we do is we design these systems. They are real-time optimization where you batch requests for 30 seconds, then you optimize. While you are optimizing your batching request, and then the next time period, you will optimize again. And you need to keep track of two things, obviously, when you do that. What is the state of the vehicles? Where are they? Where they will be going? And then once you're done optimizing, you have to tell these vehicles what to do for the next step. Now, how do we optimize? What we did was essentially using a sophisticated column generations to do that. And so this is the master problem. We are minimizing waiting time, making sure that we're covering the riders, making sure that every vehicle has a single route. And one of the difficulty here is that because we have only 30 seconds, sometimes you are not able to serve everybody. And so there are some of the customers that are not being served. And what we do to address that difficulty is to penalize those who are not served. And therefore, and this penalty is increasing exponentially. So we make sure that very soon they will be actually served by the system. So that's a master problem, which is reasonably small. The real difficulty is the pricing problem. And why is it difficult? Because you have to minimize waiting times, and waiting times are not easy to minimize because it's only when you have chosen the route that you can really evaluate the waiting time. So most of the techniques like constraint shortest path don't really work well in that context. And you can also not really discretize time because this is a massive number of people over a long period of time. So what we do is that we have dedicated algorithm to do that using a lot of the mathematical properties to prune the search space and generating routes that are very diverse. So that's how we actually deal with this problem. So I want to show you a visualization of what this system does. I always ask my students to build visualization because that's how we understand how the algorithm work. And so what you see here is New York City, rotated, 90 degrees. And the red bars are people waiting. The blue lines are vehicles with people. The other lines are vehicles which have nobody inside the vehicle. They are going to pick up a particular customer. And you can see that the system seems to be working really, really nicely. These are the results that we had. We could, cover 100% time, 100% of the rider with 2,000 vehicles, and a waiting time of 3.6 minutes, which is, pretty good for the scale of this problem. Now, I was very happy until I asked my students to do one more visualization. I asked them, well, we need to show how well we are utilizing these vehicles. So what you're going to see in this video is something that I should not actually show you because this is a little bit embarrassing. But all the blue dots here are going to be the idle vehicles. And I'm going to show you how they are evolving over time. And so this is, like 3,000 times the speed of this 2 hours optimization. And what you can see is that in the middle of the city, the vehicles are very well utilized, but all the vehicles in the north of the island and in the south are actually not utilized. And that's because they would not be cost effective to dispatch them because the waiting time would increase too much. So they basically stay there and do nothing. And we actually work with a much smaller pool of vehicles. And so obviously when I saw that, I said, okay, so we have to fix this particular problem. We have to make sure that the vehicles are at the right place at the right time. So what did we do? So the first thing we did was changing the overall framework such that from time to time, we have a particular module here. This is the MPC model, the model predictive control module there, which is going to work at a coarser granularity, but decide how to relocate the idle vehicles. And so this is, and I'm going to explain to you how it works, but this is a visualization of how well it works. So now you see the system at a particular point in time. You don't see many idle vehicles. There are some in the south part of the island, some in the north part of the island. But you're going to see they are not doing anything. So you can expect that, oops, at this particular point, they are basically being relocated to another part of the city. Not all of them, because some are going to be useful for the next steps, but many of them have been relocated to a part of the city where they can actually be useful. And that's what the model predictive control algorithm is doing. So let me go into a little bit of the results, and then I can tell you a little bit how it works behind the scene. But when we did that, we had about a 30% improvement in the waiting time. So we are really improving the system, significantly. And this is especially true for the instance, which are the largest one, where really the waiting time was higher before. So the instance which have about 60,000 people during 1 hour. So how did we? The other things that I want to mention, and this is also important, is that we did that without actually creating unfairness or bias inside the various zones of the city. So everyone is roughly the same waiting time. It's not that we are taking vehicles from poorer part of the city and relocate them to the part of the city that are richer and have more demand. The waiting times are well balanced. So how did it work? So the first thing that we did was working at a coarser granularity at the zone level, and also we don't optimize this relocation very often. It's only every 5 minutes or so, instead of optimizing every 30 seconds. And then we forecast the demand using a vector autoregression technique. And then we have the model predictive control that use the demand forecast to rebalance the vehicles. And it does that in two steps. First, it rebalances the vehicles in the zone, and then it assigns specific vehicles. So I'm going to skip this, but essentially what the forecasting model does is predicting the demand from zone to zone. Since some of the zone to zone demand is very sparse, we first do a first step where we predict the demand in a zone, and then we use historical data to distribute it. This is the zone balancing model predictive control algorithm. I don't expect you to understand, because I'm going to go very quickly. But roughly speaking, what it does is keeping track of the vehicles that are moving, with people, with riders, the one who are empty, and the requests which are not served. And then you have the traditional constraint that you expect, right? So flow conservation for the request, flow conservation for the vehicles, and we maximize the number of requests that we can serve, and we minimize the relocation cost. Once we have decided the zone-to-zone assignment, we assign the specific vehicles, and this is what you see there. That's a very simple MIP problem, because it's essentially covering the demand and making sure that one vehicle is only reallocated at most once. So, so in a sense, this was a very nice result. But recently, we actually recognized that the longer the horizon that we are working, the better results were becoming. But since we have only 30 seconds to optimize, we could not optimize that in the right time. And so the key idea that we had was to actually learn the relocation model. So instead, we let it run for a long time, and then we have a machine learning algorithm which is actually learning what it does. So, and this is this concept of optimization proxies that we are using all the time now. We learn optimization model. So given the current state of the system, we predict the relocation decisions. And to do that, we use kernel support vector regression techniques, which are a little bit more robust than deep learning techniques in this particular context. And so, and once you do this, what you can see is that now you can actually optimize essentially in the same time. You can get exactly the same quality using the machine learning algorithm that using the exact optimization model almost. But now you can also use it for longer period of time and improving quality. So this closing the loop is what we really call now end-to-end learning and optimization. So you basically use machine learning algorithm and optimization, embedded into each other, and you actually learn optimization models as well. So that's the first thing that I wanted to talk about. Now, let me talk about the second topic, which is optimization of over preferences. And this is an entire area that we have been working on, which is this on-demand public transit system. So I'm going to start by motivating what we are doing there. And then I will tell you one of the critical things that transit agencies are worried about, and then how we can overcome that particular challenge. So what we are trying to do in that space is trying to do what Uber and Lyft has done for taxi services for public transit. So really using technology and analytics to design and operate the next generation of transit system. So the transit system that we are designing are going to be multimodal and on demand. So you still have some fixed routes for rail and buses, but they are going to be much shorter and much higher frequency. And then you will have shuttles, which are going to be on demand and going to serve this first and the last mile problem, which is the real problem that has been plaguing all the transit system around the country and in many other parts of the world. So I'm going to show you a little bit of little video so that you understand how these systems are designed, operated, and used holistically. So this is done by one of my undergraduate students. So one of the key things that this video is trying to tell you is that the system is really integrating these on-demand services and the fixed rail. It's designed, and I will talk a little bit about this, holistically and operated holistically. Everything is integrated, right? So this is one of the first simulation that we did for the city of Canberra in Australia. And this is telling you how the system works overall, right? So that's what the system does. Once again, blue, the buses are blue, red are the people waiting. You see some people here on the left-hand side. So some people are waiting there. They are picked up by this shuttle. This shuttle is going to go to the bus stops there, and the bus is going to pick these people up and bring them to the next hub where a shuttle is waiting for them. So when you look at this, you can see all these shuttles, kind of busy bees picking up people and coordinating with the bus lines. So this is what these systems are doing. And I will show you in a moment the same thing for Atlanta. When we did this for, so the key point here is that this is a system which is on demand, almost door to door. And it addressed the first and the last mile problem because it's on demand. But we also make it multimodal such that we minimize congestion and we maximize economy of scales. That's how we can have a sustainable business model. So we have fleets of trains, fleets of buses and shuttles, and we are integrating as well bikes and scooter right now, and there is their own issues. We can electrify the entire system because we control the fleets, and therefore there is no range anxiety. And the business model is sustainable because of these multimodal aspects, and therefore we can operate the system for a price which is an order of magnitude cheaper than Uber and Lyft. And I told you that already. It's planned and operated holistically. So let me show you the kind of benefits that we had for the city of Canberra. Last time I checked, it was in procurement there. Essentially, we could decrease the time by about 50%, the transit time, and we could actually decrease the cost by also 50%. So this is very significant there, partly because this is a very wide geographical area, and therefore the bus lines were very, very long. And so that's how we could both at the same time decrease the budget and improve the quality of service. What you're going to see now is a completely different case study. This is a University of Michigan transit system, very small, like 5 by 5 miles area, but 50,000 students a day. And once again, you're going to see the buses in blue, people in red are waiting. That's the existing system a few years back. and 3,000 times the speed. So you can see that these buses are full along the, the connection between the central campus and the North Campus, where the College of Engineering is located. Same thing for the Atlantic Center. And what I want to show you is before and after, this kind of counterfactual studies that I like to do. So this is the existing system, at 8 a.m. in the morning. And what I want you to focus on is look at these buses. They are essentially running empty there. They are very, heavily used across the main corridors, but for servicing the last and first mile, they are not very effective. They are running empty. This is the evening, and in the evening, the frequency of the bus is twice as long. And what you can see now is that the buses are, they are serving, multiple people at the same time, but no people are waiting for a long time. So you have this trade-off between either, I serve a lot of people, but they wait a long time, or I have a very good response time, but then the buses are essentially empty. And so when you do an on-demand system, what you do is you only keep the bus lines between on the high density corridors, and then you have once again these shuttles that are operating the system for the first and the last mile. This is all the ride share as well. You can see the shuttles there. They have sometimes multiple people in them, and so this is automatically done by the system as well, using very similar techniques that I've shown you before. Now, this is Atlanta, same thing. We did, you can see all the shuttles that we are using. We have about 1,000 there in the simulation. And we have also high frequency bus line that we introduced. This is zooming, and you can see that the shuttle here are feeding really the rail and the high frequency buses. In this simulation, we know for every vehicle how many people are in there, how many people are in the trains, how many people are in the buses. It's a very high fidelity simulation using the exact schedule of the buses and the existing rail. So what I want to talk about now is one of the key worry of the transit agency. So what they typically ask us is, what if we are very successful? And this is an interesting question, right? So as academic, we probably never ask that question. What if we are successful, right? But they are very worried about successful, because then maybe the system is not sized in the proper fashion, and therefore the quality of service is decreasing. And so this is one of the things that they want us to study. They want to study, yes, but if you offer such a better service, more people are going to adopt the system, and therefore your design may not be good. So you play this game between designing the system and then people adopting or not adopting the system. And so when you do that, essentially you solve an optimization problem where part of it is a machine learning model or a discrete choice model that represent the preferences of the user. And this is a challenge to solve, obviously, because this can be a very complex structure, right? So it can be a discrete choice model, a deep learning model, a support kernel vector machine, and so on and so forth. So how do we do this? In general, what we do is we remove this model, we solve the problem, and then we find out inconsistencies between what the optimization model predicts and what really people are going to do. And then we introduce combinatorial Bender's cut to make sure that we remove this inconsistency. Now, as you know, when you put these no good cuts like this, they are extremely weak. So the key aspect of this is to make sure that we project them using domain knowledge to make them as general as possible. So let me give you an illustration of that. So one of the things that we do when we have transit system is measuring, whether people are going to like a trip or not by the time that it takes and the number of transfers. Typically, what people do in civil engineering is that they model transfer as a time penalty and so on. So you can reduce everything as kind of a how long do you take to go from point 1 to point 2, point 8, the origin to destination. And then you will adopt the transit system if it doesn't take much longer than what you would do if you would take your car. And so when you do that, you can strengthen the combinatorial cuts by using some very intuitive things like, the transit time, if I add new arcs in the system, is gonna only get better, and therefore you can remove all the arcs here in the no good that were not selected by the design. And the opposite thing is true when you remove arcs from the transit system. So you can get much stronger cut. But unfortunately, this intuition is not always true. And I'm going to give you two examples. So this is the right intuition. So if I move from the origin at the right and I'm going to the left, if I add this new link, I'm going to make the transit time faster. And so this is the intuition, right, that we had it originally. But if you add a new line, a new bus line like this, now the system, when you optimize, is going to take this person and have a very short shuttle service, and then taking these bus lines. And therefore, the time is actually going to increase, and actually you add a new transfer, which is also increasing the time for the riders. So in this particular case, the intuition is not correct. So you have to be very careful in how you increase, improve, how you lift this combinatorial Bender's cuts. And in this particular case, we were able to actually characterize it formally. So let me show you some results here on the Ann Arbor Ypsilanti transit system. This is a system which is about 1,300 bus stops, about something like 5,000 to 10,000 riders, depending upon if you take those who have already adopted the system or who could adopt the system. And what we did was looking at what it does if we look at different population segments. So Ypsilanti is rather poor, so these are a population segment which would tolerate more delay compared to the richer part of the town and the middle class part of the town. And so some of the results were actually pretty interesting. You could see improvement in adoption by about 15% or 10% for different population segments. And most of the system now can be operated at almost, some of them at a profit if we use a lot of different hubs and delay a little bit everyone. Otherwise, they're very close to profitability, which means that the business model is sustainable. And the combinatorial cuts here for capturing what the machine learning model does are bringing exponential improvements in efficiency when you lift them. And so we can really solve this design problem now in reasonable time for a mid-sized city, which was not obvious initially. So this is also telling you that one of the things that we can do is that we can actually give accessibility to people who didn't have accessibility before. This is one of the main goals of the mobility project that we have, give accessibility to a poorer population. And this is what you can do by having this on-demand multimodal system and taking into account the adoption. So in this particular case, we want to be sure that everybody can access the jobs that they are interested in less than 40 minutes. And you can see that we have a large number of adoption there as well, as well as some people who are not adopting the system because it's a little bit too long. We still improve compared to the existing system, but not enough for people to adopt the system. So that's what I wanted to tell you on this particular use case. What we are trying to do here is incorporate this very complex machine learning algorithm inside the optimization model by using these lifted combinatorial cuts. So let me move to the next step now, which is learning over physical systems. So it's going to be completely different now. I'm going to move from mobility to energy system. And I know many of you are working in this space, so some of these things are obvious to you, but power system is the largest machine on Earth. Just in the United States alone, every year we are transmitting about $400 billion of electricity. And it works. So we have, it's very reliable, except sometimes in Texas. But because of connectivity, reason, as you know. But it's a fundamental success for optimization. It uses almost every technology that has been invented in optimization, and similarly, it's a huge success for machine learning and forecasting. In addition to all the engineering which comes in actually building this grid, right? So this is a really massive success for industrial and system engineering and for engineering as a whole. Now, the times are changing because of renewable energy, right? So this is one of the partners we are working on, MISO. And MISO is this transmission operator which covers everything from Canada to Louisiana. So it's a very thin part of the United States, but it covers everything from the north, where it can be really cold, to Louisiana. And one of the goals is to move the share of renewable from about 17% to about 32% in the next 9 years. It's a very challenging goal, especially because they have a lot of uncertainty due to this renewable, but also what is happening behind and in front and behind the meter, right? So people are now charging their cars, they are using solar panels, and that makes the load much harder to predict as well. So this new reality is that you have a lot more stochasticity, and this is the kind of forecasting errors that they are making. And you can see that compared to the historical value, the errors that they are doing today are about 4 to 6 times higher. And so they have a real challenge now in operating the system because the unpredictability is much higher than they are used to. And since they want to further increase the share of renewable, this is going to make it, the forecasting and the optimization even more challenging. But it's also a very nice opportunity for machine learning because the networks are evolving very slowly. So you don't change the lines and the generators every day. And so you're solving very similar problems every day. And so, all the market clearing algorithm from the unit commitment to the look ahead commitment and the reliability commitment to the OPF are basically on the same network with different instance data. So you have a tremendous opportunity for machine learning because that's what machine learning does well. But the challenge here is that we are dealing with engineering problems. We are not dealing with a computer vision problem here. So we have physical and engineering constraints that we have to satisfy, and the system has to be reliable. So what we are doing is we are solving an empirical risk minimization problem in the language of machine learning, but under constraints, under these physical constraints. And so, most of you probably know these are the power flow equation. This is optimal power flow. That's the kind of the canonical example in this field. And it's highly nonlinear because of the physics, Ohm's law. But you also have engineering constraints that are limiting what you can really do. Have constraints on the voltage, constraints on the thermal limits for the lines. And so you have to take those into account when you do machine learning. So this is one of the things that we have been working on for a couple of years now, is this idea of doing constrained deep learning. So we do a deep learning system, but we also model all the physics inside the deep learning system. And we try to make sure that the constraints that are coming in these systems are actually violated as little as possible. Now, how do we do this? So we are basically using concept from optimization. We are using Lagrangian duality, kind of in expectation, because that's what machine learning is doing, right? And we are iterating 2 steps. So we are basically assuming that we have a certain weight for every one of the constraints, and we learn the OPF using these particular weights. But then we are actually looking which constraints are difficult and which are not, and we are updating them, and we are iterating this this process. So typical, subgradient optimization using for solving the Lagrangian dual. But the key interesting thing is that one of these steps is actually a machine learning problem. We are actually learning a solution to the OPF there. And so the last step in general is to restore feasibility by using very specific types of load flow, such that we can make sure that all the constraints are satisfied. This is typically what we do. We use machine learning to get very good predictions. They may have small violations of the constraints, and then you use a very quick load flow to restore feasibility. So let me show some of the results here. So these are experimental results on the French transmission network. It's one of the best engineered network in the world. And what you can see here, you see the generation. The generator are ordered from left to right in their generation, the generation that they are committing to. And you can see, and so this is the generation that they have, and you see the error there that we are making. And the interesting thing is that this error here is about 2 to 3 to 4 orders of magnitude. So we really can very, very accurately predict the solutions of the OPF for various instances. This is the accuracy that we get for every one of these measures for real power, reactive power, the voltage magnitude, and so on. And you can see that the errors that we are making are really, really small, and this is in nominal values. One of the things that I want to show you also is the kind of speed that we get. So we can train these models now very effectively. Actually, the latest result that we have is that we can train them in about 30 minutes. And you can see that once we have been training them, we basically can solve these things in a couple of milliseconds, instead of taking about 1 minute for one of these systems here, which is the French system at a high voltage plus a detailed version of one of the main regions. The other things that you see in this graph at the bottom is the kind of violations that we have for the constraints. They are really tiny, very small violation, which are once again expressed in nominal values here. So now this is a very ideal problem, right? So in practice, we have to do a lot more. We have to actually make sure that the system is reliable, is resilient against failure. And that's what I want to discuss, how we actually learn the same problem, but when the problem is really modeling what we do in practice. And so this is security constraint OPF. That's what, MISO, for instance, is doing. So you assume that you're at a particular point, you lose a generator, you go a little bit outside the region that you want to operate on, and then you restore this reliability that you want. So how do you do that? Typically, we use this n-1 contingency. So we are assuming that we can lose any generator. And we make sure that we optimize the nominal case, and we make sure that we can restore feasibility, whatever the contingencies which is happening. So we have two things that we compute essentially, is the pre-contingency at every one of the generation at every one of the buses, but we also compute the post-contingency if we lose a particular generator for a particular contingency S, okay? So we have these two things that we need to compute. So at a very abstract level, what you do is you compute an OPF the way we have done it before. These are the first two lines here. But then you have all these contingencies, and based on the nominal value, you want to be able to recompute something which guarantee feasibility if you lose one of these generators. So that's at a very high level. Of course, in life, things are more complicated because when you are using a power system, behind the scene, there is a lot of control systems that are actually reacting to whatever is happening. So we have to model that inside the optimization model as well. We have to somewhat model what the control system is doing without capturing the dynamics, because that would blow up the optimization completely. So what do we do? So we look at the primary control. So this is when the reactors are all reacting. So this is, for instance, in Europe, if you lose a generator, let's say a nuclear generator in France, the entire generation across Europe is going to react. And then secondary control is going to basically make sure that the generator in France are picking up the load. So when you look at this, what is really happening is that the generators are going to react to a signal, and they are going to react proportionally. And same thing here, except that this is a smaller set of generators. So this is what is happening. So the post-contingency is going to be the pre-contingency plus a certain amount of generation. That generation has been provided before. You have reserve constraints that you can use. But then you have this signal, and every one of the generator is reacting proportionally based on some participation factor. Now, this looks nice, but this is also a little bit more complicated than that, because we also need to make sure that if a generator reaches its limit, it's not taking, it's the amount of power that we have to deliver from the other ones has to be readjusted. So the proportional response not only depend on this signal and this factor, they also depend on the maximum reserve that every one of the generators are using. So you have these disjunction constraints here, which is really, really annoying. So that's modeling the system as a whole. Once again, don't pay too much attention on the details, but I hope that I gave you the intuition of what we need to do. So this is the kind of algorithm that we are using and behind the scene to do things like this. So you have the nominal case and a subset of the contingency, and we optimize. And then we check if there are a contingency that are infeasible that we need to address. And then we bring them or part of them inside the optimization model, and we re-optimize. And we do this until we get to a fixed point. The interesting thing about power system is that you don't need that many of them to actually converge to a fixed point, but you need to identify them on the fly. And so one of the things that we have been doing for solving these problems now very, very quickly is that we have basically replaced the optimization model, which is heavily complex, by a machine learning model. So we are using exactly the same scheme, which is heavily used in optimization, right? So this column and constraint generation. But instead of using an optimization module, we are using a machine learning module. But we still essentially do this feedback loop between solving the problem, in this particular case, approximating the model, and then introducing these contingencies. And obviously, once again, that means that we relearn the model on the fly incrementally to adjust to the new contingencies. So the results of this are pretty spectacular in a sense. So we were very, very pleased. You can see how well we are able to follow the generation as the load is increasing. These are very nonlinear patterns of the way the generators are moving on some of these. This is based on the French instances as well. you can see how nicely we are following what the generator is actually doing inside the optimization. So we are capturing this nicely, this very nonlinear behavior. These are once again the predictive errors that we are making. So when we are for the large, most important generator, once again, we have errors that are about 2 to 3 orders of magnitude smaller than the actual nominal generation. Once again, we have to restore feasibility for this. So we use, once again, a load flow. We're trying to find the dispatch of the generator, which is as close as possible to the prediction, but which satisfy all the constraints. And we can do this extremely fast and with very little cost increase. So you see, once again, the cost increase in percentage is like 0.06 for this particular instance. So that means that we are really, really close to the optimal solution. And we do this at a fraction of the time, right? So once again, 2 orders of magnitude faster than the column and constraint generation algorithm. So that's the second, that's essentially the integration of machine learning and optimization, and that I wanted to talk about. Now, in the last couple of minutes, what I want to talk about is a completely different problem. And once again, what is interesting here is that this is a problem which is linked to the census data. And what I want to talk about here is the fact that our community, optimization and industrial engineering, in a sense, has a lot to offer to problems which are typically not seen as problem of industrial engineering. And so what I'm going to show you here is really a data science problem, but you're going to see that optimization techniques are critical to make it work in practice. Okay, so let me introduce the problem to you. So this is something that the United States is doing every 5 years, if I remember correctly, maybe not, but very often. And so it's actually, computing, and we were doing that, last year. And so one of the things that you're trying to do is to find out what is the population and various features of that population in every one of the counties and the tract level across the country, right? So you want to know how many people live in this county, what is the average, salary of those people, how many cars do they have, and things like this. Now, the US has a regulation, Title 13, which means that you cannot release identify information. And as you know, even if you, kind of remove some of this information or try to make it, private by using basic techniques, because you can link that to all the data set, you can recover a lot of identify information. So there was a beautiful paper by people at MIT saying that if you know if you have a trace of 3 mobile phone connecting to the antenna, you can actually identify uniquely who these people are. And so you have to be very, very careful. Now, so this is what you need to do, right? So you need to be able to have people asking query on this census data and give an answer, but making sure that that answer is going to be, private, doesn't release any information on any individual. And the typical way to do this is that you take your query, you ask the database, and then you randomly assign noise to that answer such that it becomes private. Okay? Now you have to do that such that people cannot recover this information by using any other data set. And there is a beautiful framework to do that, which is called differential privacy. And at the high level, what this does, it makes sure that if you ask a query on a database, let's say with these people, and this is the probability of the answer since the mechanism is randomized. And if you add one more person, you cannot have a very different result. So the difference between a database where you add or remove one person is essentially, the query is going to have the same answer, modulo a small epsilon. Okay, so this is what differential privacy does. And so this has been used in a variety of settings. Google and Apple are using this. And typically the way you do this is that you analyze the sensitivities of your query. If you add one person, how does it change the query in the worst case? And then you add a noise which is calibrated by this sensitivity. And so when the variables are continuous, you use Laplacian noise, for instance, and that will guarantee differential privacy. And when you are actually using integer values, you can use its geometric counterpart. Okay. Now, when you look at the census data, obviously you are, what you want to release is also hierarchical data, right? So you're looking at the various counties of, this is, I think, Indiana, Ohio, but you also want to actually release the data for Ohio as a whole, and you want to do that for every one of the states. So this is a little bit what you want to release. You want to say, hey, the US has that many people, Georgia has that many people, New York has that many people. Inside, a Cobb County, which is a county in Georgia, you have that many people. Inside, Fulton, which is where Atlanta is located, you have that many people. And so these are the true counts, and you are releasing the noisy counts, which are obtained by putting this noise, geometrical noise, on every one of them. Okay, so this looks nice, but this is where theory and practice start differing, right? So so now when you look at this in practice, what you will have is that some of these counts are going to become negative. So you're going to say there are -2 people living there, and then there is also a problem of some of the domain constraints are going to be not satisfied. So if you sum all the counties, the noisy counts inside Georgia, you may not have, that may not be equal to the noisy count for the state as a whole. So you have to start satisfying these constraints. Otherwise, the results don't make any sense. And so there is one property of differential privacy that you can use for that, which is called post-processing immunity. So once you have something which is private, you can transform it using a post-processing step in any way you want, provided that you don't look at the real data. And that's what I'm going to show that we are going to use. So what we want to do is to start saying, yes, I want these noisy counts, but I want to change them such that I'm recovering all the problem constraints, all the domain constraints that I have. So in this particular case, I want to make sure that the sum of these two noisy counts is equal to the noisy count that is there. Okay? So in a sense, what I want to do is define an optimization problems which take the noisy count and try to find post-process counts that are as close as possible to the noisy count, but satisfy all the domain constraints. Okay, so this is beautiful, but unfortunately, this is a problem which has something like 350 million people, so it's extremely difficult to solve. Okay, so what are we going to do? How do we scale such that we solve these problems for the Census Bureau? And the key point here is that we can use a very, very interesting dynamic programming algorithm to do that. We can use a bottom-up phase, which computes the optimal cost for various values for various potential, costs for every one of these, or every guess for this particular, at the higher level of the hierarchy. And then we can do a top-down phase for recovering these costs. So this is what we do at every one of the level. You solve this optimization problem. So if you guess that at the parent, the value is V, you can actually find what is the best cost that you can get for the noisy count. And this is a very local optimization problem now that you can solve. Now, still, this problem is very difficult to do, but the key point is that this cost table a very nice property. They are piecewise linear convex, and therefore they can be computed nicely and decomposed at every level of the hierarchy. And therefore, you can solve this problem in polynomial time. Now, in practice, this is a little bit more complicated, and I won't have the time to actually tell you some of the tricks that we are using. But instead of using counts, we are using cumulative counts. The problem becomes non-convex. So the way we do this is that we flatten the entire hierarchy, and then we can have, again, a very nice dynamic program. I want to show you some of the results, which are also very interesting. So the top-down algorithm that you see there is what the Census Bureau is actually using. And this is the latest algorithm that we have produced. So we have 3 orders of magnitude in this particular case improvement in efficiency. This is also on data set which are coming from the census data and also from the taxi data set in New York City that I talked about before. So once again, you can see that these algorithms using these sophisticated optimization problems can make a huge difference in terms of the accuracy and also in terms of the speed of these algorithms. This is the improvement in accuracy that you see compared to just using simpler algorithm. So this is what we can do there by using really OR technology for improving these data science problems that come from very different areas. Now, I want to finish by showing you a little bit of a challenge that we face when you do this. So when you do this post-processing algorithm, one of the things that you do is you introduce some biases. And this is very, very delicate, because some people are going to use this census data to make decisions afterwards on allocating funds, deciding if you for schools, in deciding if people are if you put let's say 2 languages on ballots and things like this. So you have to be extremely careful, and we are spending a lot of time now looking at what is really the nature of these biases and where do they come from. And so the biases are really saying, is the expectation of the mechanism close to the real data or not? And so one of the things that we have shown is that really the problem comes from these non-negativity constraint, bonding constraints. It doesn't come from the equations themselves. And so you have to be really careful about those. And we are working on optimization techniques to counteract those as well. So let me conclude now. So I think one of the things that I hope to, I gave you is a sense that there are tremendous opportunity for our field in data science. And in particular, I'm showing you that you can integrate machine learning and optimization in very sophisticated way to actually address some of the challenges that we face in engineering. I also hope that I've shown you that, our field, there's a lot of techniques that can be used for problems that are faced by other disciplines, more standard disciplines like computer science, for instance, by using sophisticated optimization techniques in those data science fields. So summary, you've seen these case studies. I want to tell you that there are a lot of opportunities there. I think we are just tapping the tip of the iceberg. There are many more things that we need to discover. There are challenges in all aspects, how you combine really optimization and machine learning, or you scale these techniques such that they work on really large problems. And one of the things where I think we have a lot of opportunity is decision-making under uncertainty, because those problems are extremely complicated from a computational standpoint. And I think by merging, data science, all this end-to-end data science, learning and optimization, I think may bring a lot of value to these problems. So thank you very much for listening. And I hope that, I give you some of, some ideas of what we are doing, and I'll be happy to take, obviously, any questions that you may have. So thank you very much.